So, we have been looking at the generation of space groups and the way in which the equivalent points arrange themselves in the unit cell. The simplest of the space groups is P1 bar, of course P1 being redundant, it has no symmetry operation. In a triclinic system, P1 bar is only allowed space group other than P1. And this space group has a center of symmetry. The presence of the inversion center is shown with respect to the equivalent points here. So, we have taken the object to be in the shape of a comma. It could be a molecule, an atom, ion or whatever. And the plus sign here indicates that it is in the forward direction and the minus sign indicates it is in the backward direction. So, we did the generation of the equivalent points, found out the presence of centers of symmetries at different positions other than the origin. One of course due to translation along A, another due to translation along B, and halfway points getting the centers of symmetry. And as a consequence of that, this symmetry operation which goes outside of the unit cell can be brought into the unit cell by one unit translation along A, one unit translation along B. So, it is actually representing two such units, two such objects in the unit cell. We call them the number of molecules or whatever, number of units, number of objects inside the unit cell. In this case it is 2. So, we extended this to the monoclinic system, the point group symmetries being 2 m and 2 by m. The point group symmetry 2 gives rise to, in the primitive lattice, 2 cells P2 and P21 by m, P21. So, the presence of the two-fold axis and the presence of the 2-1 axis we discussed, and we see that these equivalent points get generated as are marked here. Then we also looked at the possibility of the centering of the lattice in a monoclinic system, and C2 and C21 get generated. We also indicated that C21 can be changed to C2. This is just a recollection of the previous class. Then we introduced the next symmetry elements. After the point group symmetry 2, we have the point group symmetry m. We looked at the monoclinic symmetry primitive, and then we went further and looked at the monoclinic symmetry PC with P is the primitive and C is the glide plane. So, then we looked into the mirror symmetry operation with respect to the C centering, and then we had arrived at this point where we had the CC. Now, so just keeping the logic of arguments going, if one looks at this particular diagram, suppose you are given only this diagram and then the positions of the equivalent points. In this case, of course, both the positions of the equivalent points and the symmetry operations are given. But suppose you are given only these equivalent points, in principle one should be able to get to the equivalent points. One should also be able to get to the equivalent points once we are given the symmetry diagram, and that is what you will find when we go and discuss the international tables later on. But at this particular moment, in this case, suppose you are asked to find out the equivalent points, how would you go about it? Of course, I have already marked 1, 2, 3, 4 for your convenience. So, there are 4 equivalent points in CC. So, the way the objective way in which we go is to take this point which is marked as 1 as x, y, z corresponding to the coordinates x, y, z. Then because of first you operate the C centered lattice symmetry, that means the lattice symmetry gets the prominence. So, once you operate the C centering, that means there is a half plus x and half plus y added to the x, y, z. So, suppose we call 1 as x, y, z, then we have a point number 3 which is marked here, which is due to the C symmetry operation, which is half, this is the A direction. So, half plus x, and then there is the B direction half plus y. So, we get this point. So, these equivalent points 1 and 3 are generated by the C centered lattice. The the glide operation, which is now coincident with the origin. So, that is the glide is perpendicular to the origin, and therefore, we get a glide operation which takes this mirror symmetry, and in the direction coming towards you along the C direction, it adds a half. So, the glide plane C now operates the mirror on 1 and then adds a half. So, this is the point 2. So, we therefore get this as x x, and this is the mirror symmetry. So, we get x y bar half plus z. So, therefore, we can actually arrive at the equivalent points, the first equivalent point being x y z, this is half plus x half plus y z, and this is x y bar half plus z. Now, what happens to this particular point? This particular point can be translated by 1 unit, and if you translate by 1 more unit, it goes out of the unit cell. So, but in this case, if you translate it by 1 unit, it comes to this point half plus this object. Now, what you see here is that there is a, by definition, whenever there is a symmetry operation at 0 and the symmetry operation 1 unit translation, the same symmetry operation will develop at half position. So, using this half position, the C glide, we can generate its corresponding C operation, C glide operation. So, that means this now goes into a mirror symmetry, and then it adds on a half in the direction of C, and therefore, we get to this point 4. So, one can therefore, in principle, given this picture, write down the equivalent points. And in the next slide, I have shown what are those equivalent points. Those equivalent points are x y z, x y bar half plus z, x plus half, y plus half z. So, as you see that this is the C glide operation, and this third is the C centering operation, and then the C glide operation on this object, which is due to the C centering. We now operate the C, sorry, this is due to the C glide, we operate on the C glide the C centering operation. So, this goes to x plus half, y bar plus half, and z plus half. So, these are the 4 equivalent points. So, the take home lesson here is that given this diagram, in principle we should be able to write the equivalent points. So, this the next example we can take up is given the equivalent points like here, given the equivalent points as is given here, you will be asked to determine the space group. So, if one asks that question, in this particular case it is a very simple example. In principle, you should be able to identify the space group. See, you see here point 1 and point 2, they are related by what? They are related by a two-fold axis perpendicular to the y direction. So, you have a two-fold symmetry, and you also do not have any half plus x half plus y or half plus y half plus z, or for that matter half plus x half plus z. So, that means that the centering is not seen. Generally, since the monoclinic symmetry is C centered, you should have equivalent points half plus x half plus y, and that since that is not appearing, this is a primitive lattice. So, the first conclusion is examine the equivalent points, find out if there are any half translations associated with x or y, or in this particular example of a monoclinic symmetry, and then you see and conclude that it is a primitive lattice. So, we have found that it is a primitive lattice, it has a two-fold symmetry. Now, if you look at the point number 3, it is a mirror operation perpendicular to the B direction. So, we have a two-fold symmetry along the B direction, a mirror plane perpendicular to the B direction. That means it has, and it also has a center of symmetry equivalent point, which is x y z going to x bar y bar z bar. So, we are now looking at a centrosymmetric space group. So, the logical way to go about when equivalent points are given is to first see whether it is the type of lattice. So, suppose it is a primitive lattice like here, identify the primitive lattice, then look for the existence of x y z, x bar y bar z bar. That will tell us that it is a centrosymmetric system, and then you look for the operation of the two-fold and the operation of the mirror symmetry as we see here. So, this is very easy to conclude the space group is P2 by M. So, once we conclude the space group is P2 by M, in principle we should be able to generate an equivalent point diagram and also a diagram for the symmetry positions. This is something which you will have to practice, taking some examples of other space groups. I have taken an easy example for you to illustrate the whole thing, and that is given here. So, you see that there is a two-fold axis along the B direction, So, the two-fold notation is here, the two-fold notation is here, because this is along the B direction. We are giving the AB projection. We are looking down C. So, this angle is 90 degrees, it is a monoclinic system, primitive lattice, and then we have these 4 equivalent points around the center of symmetry. So, 1, 2, which is generated by the two-fold axis symmetry, then the mirror symmetry from here goes there, and then the center of symmetry operation takes it over there. So, therefore, these are 2 and these 3 of them can be brought inside by translational symmetries as we discussed before. That is point number 4 will go undergo a translation along A and translation along B, we get this, and so also this one translation will bring it here, this is one translation will bring it there. So, there are 4 equivalent points in the unit cell. We also have marked the mirror symmetries as dark lines here. They appear at the cell edges as well as at the central point, and the axis is about the y direction. So, no other thing happens except that once the center of symmetry develops here, there will be a center of symmetry up there. Now, because of the presence of the center of symmetry up there, this will also see now a 2 by m operation, and therefore, we have these kind of equivalent points. I will leave it to you as a home exercise to find out the presence of special positions in this particular space group. Since we have discussed the special positions in detail in the earlier classes, it should not be very difficult, but then it will need some thinking. Are special positions allowed in this space group? If so, how many of them are allowed? And when we actually go into the examination of the international tables entries, you will see that all these things are given in the entry, and it is just a question of interpretation of the entries in the right context. So, this therefore now brings us to the understanding of 2 of the symmetry elements. In fact, today we have seen the CC, the presence of the mirror point group symmetry. We have also seen the presence of 2 as well as a perpendicular mirror. So, this space group analysis now tells us about the fact that we are now looking into the center of inversion related space group. All the earlier space groups PC, CM, CC belong to the non-center symmetric space group. So, what really happens is that when objects get into these kinds of space groups, there is always a possibility that they will have a homocentral non-center symmetric presence in the structure. Some of them, for example, in the case of an organic molecule, they may even have a asymmetric carbon, but it is not necessary that the asymmetric carbon should be present in these 3 symmetry systems, because we have a mirror. So, the presence of the mirror can always invert a non-center symmetric or an asymmetric carbon as well. So, what we have to look for is the fact that there is no x bar, y bar, z bar coordinate system in these 3 space groups, and therefore, these 3 space groups belong to the non-center symmetric space groups. Crystals have a tendency to prefer and crystallize in a given space group depending upon their symmetry, as we already saw. The molecular symmetry decides what kind of a crystal symmetry it should occupy. So, having kept that in mind, we will now go further and discuss the presence of the 2 by m symmetry. We have already seen the one with the primitive system. Now, we have to see the combination of the two-fold axis with the mirror. Now, when we are talking about the presence of the two-fold axis with the mirror, something very interesting develops here. So, you take for example, this is the B direction, and your two-fold axis is along the B direction as is indicated by the half arrow. And at the origin we have an intersection of the 2-1 axis and the mirror. So, this is the origin O, at which position we have the intersection of the two-fold axis and the mirror. Now, the presence of the two-fold axis and the mirror generates equivalent points, and we have taken a one-dimensional 1 unit example along the B direction. You see that the operation of this, the mirror operation on this particular point will take you over there, and the 2-1 screw operation will go up here, two-fold rotation and a half translation, and then the two-fold rotation and half translation will bring this object, which is now 1 unit translated of that object, and these 2 are now, you see that there is a center of symmetry which develops at this point. The point at which the presence of the center of symmetry is found in the 2 1 by m system is 1/4 removed, because the mirror repeats itself at half position along the axis. So, the center of symmetry repeats at 1/4. The convention in crystallographic nomenclature is not to have a center of symmetry. If there is a center of symmetry in the system, it should coincide with the origin. That is the nomenclature, and therefore, it is a rule that the center of symmetry becomes the origin. That means we have to now shift the this O to this position. When we shift this O to this position, you see that we now develop a 1/4 position mirror. So, the mirror now, suppose this is our origin, the mirror now comes at 1/4 removed from the center of symmetry. And then we will also have another mirror which comes at 3/4 as a consequence of the center of symmetry being present at the half position. So, let me repeat, if you have the 2 1-fold and the mirror intersecting with each other, the presence of the mirror symmetry and the 2 1 screw axis perpendicular to that are shown here in the direction of the B axis. The first operation is the 2 1 screw axis. So, you take this, rotate by 180 degrees and translate by half the unit along the B direction, and you will get this object. You see that the object now is going down and this object is on the top. And this object now again sees the center of symmetry, sees the mirror symmetry here, and there is a mirror reflected operation. There is a mirror reflected operation here, there is a mirror reflected operation there at the half position, and also there is a full position mirror reflected objects. So, you have one unit translation along this direction which takes this object onto that one, and the mirror symmetry operation brings it back in. So, these are the 4 operations which we get, 4 symmetry positions we get inside the unit cell along the B axis. The fact that this happens brings in the presence of a center of symmetry, invokes the presence of a center of symmetry at 1/4 removed from the origin. The origin being the position where the 2 1 axis and the mirror plane intersect. The crystallographic nomenclature and the crystallographic follow up of rules tells us that whenever there is a center of symmetry, the center of symmetry should be at the origin 0 0 0. So, what we therefore do is we take this position O and move it to this origin. So, now O is in this particular position. If O is in this particular position, there is no other change. 2 1 screw axis is going through this center of symmetry at 0 0 0. So, the presence of the 2 1 screw is not altered because it is going through the center of symmetry at 0 0 0. What is altered is the position of the mirror plane. The mirror plane now moves by 1/4. So, if you have an operation which has a translation involved component, along with that a component which is no translation involved component, the no translation involved component moves away by 1/4 from the origin. The origin now is identified with respect to the presence of a center of inversion. So, the center of inversion or the center of symmetry in the crystal system is now at 0 0 0, mirror comes at 1/4, and then you have the 2 1 screw are coinciding with the center of symmetry. So, this therefore gives us the 2 1 by m symmetry, and this is where we have to be cautious in deciding the equivalent points, because the equivalent points now will change their phases, in the sense that if we have the 2 1 by m operation here, the mirror operation will take using this as the origin, it will take x y z to x y bar z. On the other hand, the mirror operation which is now here, if this is the 0 position, then this particular mirror operation, the coordinates will change. The coordinates will change in such a way that the presence of the mirror at 1/4 away from the center of symmetry needs to be recognized. So, this is as far as the 2 1 by m symmetry is concerned. Now, we will go and discuss the possibility of 2 by C. Again, you remember that C has a half component, half translation component. So, if C has a half translation component, then what is the way in which you infer where are the axes that will be located? For example, the 2-fold axis, where do you think they will be located? The 2-fold axis now will be coincident with the origin. Let us examine this carefully. Notice that now instead of showing the B direction, I am showing the C direction. This is very important. So, this shows now the C axis, not the B axis. See, for all descriptions of the monoclinic systems, we have taken the B axis. Here we are showing the C axis, keeping in mind that the unique axis is still B. The unique axis is still B in this example as well. So, if you now look at the way in which the symmetry operations get disposed, you will see that there is a two-fold axis which will coincide with the origin, and the presence of this two-fold axis will generate these 2 points. Now, this point 1 unit translation will go there, and this point 1 unit translation will come here. This will tell us that there is a two-fold axis at the half position as well. Now, the fact that there is a two-fold axis here at 0 and a two-fold axis at half and a two-fold axis again at this particular position will generate the C glide operation, which is now, remember, this is the C axis. So, the half translation is along the C axis. So, you mirror reflect it and translate by half unit, and this point gets generated. You notice that there is a relationship between this point, and that is the presence of the inversion center. So, the presence of the inversion center is automatically invoked, and as we discussed in the previous example, the presence of the center of symmetry now should become the origin. So, we shift the origin to 0 0 0 to the presence of to the center of symmetry. So, the O is now moved over here. So, what therefore happens is the non-translation involved symmetry element. What is the non-translation symmetry element that is involved here? It is the two-fold axis. So, the two-fold axis now moves by 1/4. So, this moves by 1/4 away from the center of symmetry. That will also generate the symmetry at 3/4. So, as is written here, 2 1 by m with screw in B direction and mirrors at B is equal to 0.5. The mirrors are now at 0.5 as is shown in the diagram, but we now know we have to shift it to the centers of symmetry. So, the center of symmetry up here now has a mirror at 1/4 and 3/4. And so also the presence of the C glide invokes the moving of the two-fold axis by 1/4 from the center of symmetry. So, the non-translational symmetry too is moved by 1/4. Now, what is the consequence of this when we generate the space group diagrams, and in what way these influences the presence and description of the equivalent points? There are two ways in which we can argue this out. See, one of the things is that we have this condition of the definition of a space group. When we say the points belong to a space group, then when we keep operating the symmetries, we should get back to the original point. Now, if you take this as the origin, the intersection of the mirror and the 2 1, your x y z will see both 2 1 and mirror. And apart from that operation, we do not have any further operation at that particular point with respect to 0. The fact that the center of symmetry develops at 1/4 position is not going to give us back the x y z. In other words, if you take this point as x y z, you operate the 2 1 symmetry on this one, you will go to that point which is what? X bar y z bar. So, you get the x bar y z bar, you get the x y z, and the fact that this has happened is because of the operation of the 2 1 screw. Then we have x y z and this point which is the mirror symmetry, which will take us to x y bar z. So, the presence of the symmetry at x y bar z and at the origin, and the presence of the symmetry 2 1, if we keep operating again one of them or operate them together, we will not get back to x bar y bar z bar. X bar y bar z bar will not get invoked, and therefore, the space group points will not complete the definition of a group. So, mathematically, in order to complete the definition of a group, it is required that we move the center of symmetry to the origin. Once we move the center of symmetry to the origin, we already know the x y z and x bar y bar z bar are two equivalent positions with respect to the center of symmetry, and the rest of the equivalent positions can be generated, as we can see when we go to the next discussion. So, since this part is a little tricky, and this is not explained in any detail in any textbooks except for this one, which is the textbook of Stout and Jensen. I thought that in fact in Stoughton-Jensen there is a mistake on one of these equivalent points as well, which I think we have corrected. And therefore, one has to be careful in looking at some of these. I think the correction is up here in this particular position. So, what we will do therefore is to see that whenever we have a translation involved symmetry that is associated with the space group, along with another symmetry operation which is a non-translational symmetry operation, or for that matter if it is a symmetry operation, suppose we go to 2 1 upon C. We will see that in a little while that 2 1 upon C will invoke translations of both the symmetry elements. So, the take home from this particular slide is whenever you have a non-translation involved symmetry element, that particular the non-translation involved symmetry element for the fact that it is a centrosymmetric space group, because 2 1 by m will translate itself to a P 2 by m point group. Since the point group is 2 by m, it will represent a center of symmetry. So, the presence of the center of symmetry invokes the requirement that we should have a center of symmetry in the system. The fact that we have a center of symmetry in the system, we have to associate that with 0 0 0. So, once we do that operation, what we have to remember is whenever there is a non-translation involved component, that is the one which moves by 1/4, and the translation component will stay along with the center of symmetry. The same is true in the case of 2 by C. You see that the twofold axis which is going perpendicular to that stays along with the center of symmetry, whereas the glide plane stays along with the center of symmetry. The non-translational symmetry element, the twofold, is moved by 1/4. Now, these two observations have to be incorporated when we now discuss the space groups which involve non-translational periodicity associated with them. Space group like P 2 by m, space group like P 2 by C, space group C 2 by m, which is also C 2 1 by m, as we have seen C 2 1 and C 2 are one and the same. Then of course, C 2 by C. We will also have the combinations of both these having translational symmetry, because a point group 2 1 by m can generate a centrosymmetric space group 2 1 by C. So, we can have two additional space groups P 2 1 upon C and also C 2 upon C. So, we will have to now examine these, and that will in fact complete all the requirements of a monoclinic space groups. So, as you see from a single center of symmetry, when we go to the presence of a minimum symmetry of a twofold and a maximum symmetry of 2 by m in a monoclinic system, 3 point groups now will generate several space groups. So, the number of space groups have now increased enormously compared to the 2 that is associated with the triclinic symmetry. Therefore, we have the condition here that the 2 1 by m operation will now shift the mirror plane by 1/4, and the 2 by C operation will shift the twofold symmetry by 1/4.